You know, usually when we talk about the AI revolution, there's this expectation that it's all about the brains.
Right.
Like you picture these massive, hyper-fast, glowing GPU chips doing, trillions of calculations a second, just getting smarter and smarter.
Yeah, it's a very human way to understand a complex technology, I think.
Exactly. It's comforting for us to just point at a piece of silicon and say, there it is. That's the AI.
We inherently want things to be centralized. We want them localized in one physical brain that we can just visualize.
But then you step into the actual reality of a modern data center, and suddenly that mental picture is completely broken.
Oh, completely shattered.
Because the real bottleneck right now, the thing keeping the biggest tech companies up at night, isn't the brains themselves, it's how those brains talk to each other.
Yeah, the industry is facing a massive, really kind of hidden crisis right now. The raw computing power is absolutely there. But the nervous system, connecting it all, is fundamentally struggling to keep up with just the sheer volume of information.
Okay, let's unpack this. Because today, our mission for this deep dive is to explore this hidden networking war.
Yes.
We've gathered insights from, well, a whole stack of sources. We've got Reddit whistleblowers in the high-performance computing space.
Which is a wild thread, by the way.
Oh, it really is. Plus some deep-in-the-weeds engineering presentations, some tech blogs, and the latest financial channel checks.
Right.
We are bringing all of this together to figure out how the tech industry is desperately trying to wire these mega brains together without, literally melting down the power grid.
And to give you the big picture context before we look at the hardware, we really have to understand the software shift that is forcing this crisis.
Right, because it's changing, isn't it?
Dramatically. The industry is aggressively moving toward what is called agentic AI.
Okay.
This isn't an AI that just, answers a trivia question or writes a poem. Agentic AI actively manages tasks. It orchestrates workflows and makes autonomous decisions over long periods of time.
Which requires a totally different setup.
Exactly. To make that happen, we are linking tens of thousands of GPUs together into single, massive clusters. And if those chips cannot communicate with each other instantaneously, the entire system just stalls.
I really want to dig into that shift because it changes everything about how a computer is built.
That does.
We're moving away from just training a model in a vacuum. Right? And we're moving toward AI agents that are constantly reasoning, fetching outside data, and executing multi-step plans in real time.
Yeah, and that shift places fundamentally different demands on a system.
How so?
Well, traditional AI training is actually very predictable. It's a heavy, continuous load. Like a freight train moving at a constant speed.
Right.
But agentic workloads are chaotic. They require persistent memory access, massive context windows, meaning the AI needs to remember huge amounts of information simultaneously, and incredibly high concurrency.
Wow.
You have thousands of different microservices trying to talk to each other all at the exact same time.
And when you look at the hardware fallout from that, it is completely flipping the script on how servers are designed.
Absolutely.
Like when AMD's CEO, Lisa Su, spoke recently at the Advancing AI 2026 conference, she pointed out this massive architectural shift.
Right, the ratio change.
Yeah. Historically, in a standard AI data center, you might see 4 of those incredibly powerful GPUs paired with just one standard CPU. The CPU was essentially just a traffic cop, slowly waving data through the intersection.
Exactly.
But because agentic AI requires so much complex orchestration and logic, that ratio is dramatically shifting. She expects it to hit a 1-to-1 ratio or even 2 CPUs for every single GPU.
And if we connect this to the bigger picture, it means the front end of the network, how data actually gets into the AI factory from the outside world, has to completely adapt.
It can no longer just be a dumb pipe.
Exactly. This is where data processing units, or DPUs, are stepping in to save the CPUs from being overwhelmed.
Ah, right.
AMD is currently deploying their Pensando Selena DPU to handle this exact front-end traffic jam.
And the performance numbers on that piece of hardware are wild. This Selena DPU delivers 1.4 times the performance of competing chips in its class, specifically NVIDIA's Bluefield 3.
Which is a massive jump.
Right. But the part that really stood out to me isn't just the speed, it's what the DPU does for the rest of the computer.
Yeah, the offloading.
Exactly. By offloading all that complex networking, security, and storage traffic, the DPU actually gives up to 22 CPU cores back to the server so they can do real AI work.
rather than wasting processing power figuring out where a data packet goes.
Yes. It's like moving from an isolated factory assembly line where everyone does one repetitive task to a corporate office full of project managers who have to constantly talk to each other to get a single project done.
That's a great way to put it.
I mean, if the project managers have to run their own mail, answer the phones, and check the security badges at the door, no actual managing happens. You have to hire a dedicated mailroom and communications team just to free them up.
Yes, and to take that project manager analogy a step further, imagine if those managers aren't just in the same building, but spread across an entire campus.
Oh, wow. Okay.
That brings us to the next massive challenge. If we are fixing the front door with smart DPUs, what happens when we step inside the house?
Right. How do you physically wire these chips together on the inside?
Exactly. Because we're talking about massive physical server racks where 72 GPUs have to be wired together to act as a single unified megabrain.
And this is where that fascinating debate is playing out among the engineers actually building these things.
I've read Reddit threads.
Yes. There are massive arguments happening right now in high-performance computing communities online comparing two absolute heavyweight architectures. You've got AMD's new Helios rack on one side and NVIDIA's Vera Rubin NVL72 rack on the other.
And the stakes here are astronomical, and you can see it in the raw specifications.
Right.
For instance, the AMD Helios rack provides 260 terabytes per second of aggregate scale-up bandwidth.
Mind-boggling numbers.
It really is.
Yeah.
It also gives the system access to 31 terabytes of HBM4 memory.
Right. HBM stands for high bandwidth memory, and the 4 is the latest generation.
Exactly. And instead of laying memory chips flat on a motherboard, HBM stacks them vertically, like a skyscraper, right next to the processor so the data doesn't have a long commute.
And because these are multi-billion-dollar contracts on the line, the engineers dissecting these specs are fiercely protective of the details.
Very much so.
In one community debate, people were aggressively correcting the record on memory speeds.
I saw that.
Yeah, a user pointed out that AMD's new MI455X GPU actually hits 23.3 terabytes per second of memory bandwidth per chip.
Which might sound like a tiny detail to some.
Right, but it is a massive deal because it slightly edges out the NVIDIA Rubin's 22 terabytes per second.
Exactly.
In this specific arms race, a tiny fraction of a percentage point in memory speed is the difference between winning and losing a hyperscaler contract.
It is a game of absolute inches. However, beyond the sheer speeds and feeds, there is a fundamental philosophical difference in how these two companies approach building a megabrain.
Okay, lay it out for us.
NVIDIA relies on a vertically integrated proprietary stack. They use their own custom NVLink 6 switches, their own network interface cards, and their Spectrum-X platform.
So they own the entire ecosystem from the silicon to the cables?
Exactly. It is a walled garden.
Which is the total opposite of AMD's strategy right now.
Very much so.
They are leaning incredibly hard into open standards. They are using something called UALoE Ultra Accelerator Link over Ethernet, paired with their Volcano 800 AI network interface cards.
Right.
And what blows my mind is that they are using Ethernet. The underlying technology that runs the Wi-Fi router in your living room is being retrofitted to run the most advanced supercomputers on Earth.
Well, the reason for that comes down to sheer economics and supply chains.
Makes sense.
Ethernet is a decades-old, globally adopted standard. Millions of factories know how to make Ethernet components. The financial argument for retrofitting it for AI is just undeniable.
It's cheaper.
Much cheaper. Estimates suggest that using this open Ethernet-based standard can save data center operators up to 33% on network switching costs compared to proprietary setups.
Here's where it gets really interesting, though. Open standards sound great for saving money, but doesn't NVIDIA's Apple-style closed ecosystem guarantee everything just works perfectly out of the box without integration headaches?
That is the multi-billion-dollar question, isn't it?
Right. Like, wouldn't you gladly pay a premium just to avoid the nightmare of mixing and matching different vendors?
It's exactly the calculation these hyperscalers are running every single day. A closed system absolutely offers a highly optimized, predictable path. When one company controls every variable, troubleshooting a broken connection or tuning performance becomes much more straightforward. You just call the one vendor. But hyperscalers fundamentally despise being locked into a single vendor because it completely strips them of their pricing power. They want interoperability.
Ah, of course.
If a startup invents a slightly faster network switch next year, they want the freedom to rip out the old one and plug the new one in without having to rebuild the entire rack.
And clearly, the open strategy is winning some massive business. We are seeing deployments at a scale that is almost hard to comprehend.
Unprecedented scale.
Yeah, AMD recently secured a deal to provide the first gigawatt of power for Anthropic's data centers starting in early 2027.
To contextualize, a gigawatt, that is the power output of a large nuclear reactor, or, enough energy to power a medium-sized city, dedicated entirely to a single AI deployment.
Which is the perfect transition to the real elephant in the room.
The power problem.
Yes, because whether a company chooses the open Ethernet route or the closed proprietary route, they eventually hit the exact same brick wall. Wiring 72 GPUs together in one rack is hard enough, but the goal of agentic AI is to scale out to 200,000 GPUs across a massive data center.
And when you do that, the power bill becomes terrifying.
Terrifying is the right word.
The scale of the power consumption is alarming infrastructure experts globally right now. Recent engineering presentations from telecom giants like China Mobile have laid out the math, and it is staggering.
What are we talking here?
A 200,000 GPU cluster consumes roughly 435 megawatts of IT power.
So we're talking about a facility that drains enough electricity to power hundreds of thousands of homes.
Just to run one unified supercomputer.
What does that even mean for a local power grid?
It means data centers are having to build their own dedicated power plants just to function.
Wow.
But here is the specific detail that keeps network engineers awake at night. Of that 435 megawatts, 17 megawatts are drained purely by the optical transceivers.
Wait, 17 megawatts? That's enough power to run a small town. And you are saying that power isn't being used by the GPUs doing the actual math. It's just being used by the little lasers and sensors passing the data back and forth through the fiber optic cables.
That is exactly correct. Just the cost of moving the data from one side of the room to the other is 17 megawatts.
That's insane.
It is fundamentally unsustainable. You cannot build the future of artificial intelligence if the cables alone are going to bankrupt your energy budget.
Right.
This is why the entire hardware industry is desperately pivoting toward a frankly sci-fi solution. Co-packaged optics, or CPO, and near-package optics.
Okay, so let's break down how this actually works. Because a traditional pluggable optic, the kind of cable you can literally grab with your hand and shove into a slot on a server rack, uses about 15 watts of power per connection.
Right.
But this new co-packaged optics technology somehow cuts that down to roughly 5 watts. How are they magically cutting the power consumption by 2/3?
They achieve this by physically removing a highly power-hungry component called the DSP, the digital signal processor. In a traditional pluggable setup, you have electrical signals traveling from the main brain of the chip across the physical motherboard all the way to the edge of the rack where the laser is located.
Which is pretty far, relatively speaking.
Exactly. That distance can be tens of centimeters. By moving the optics, the lasers themselves, directly onto the exact same piece of silicon as the processor, literally co-packaging them, you shrink that electrical path from centimeters down to mere millimeters.
So instead of using a megaphone to shout instructions to a translator across a massive football field, which takes a ton of energy, you are firing the translator and just whispering directly into the ear of the person sitting a millimeter away from you.
That's spot on. And by whispering, you eliminate the need to aggressively amplify the electrical signal, which saves massive amounts of power.
Right.
You also eliminate the DSP that was doing all the heavy lifting of translating that signal. The industry knows this is the only path forward.
And we can see this in the acquisitions, right?
Oh, absolutely. Look at AMD buying Inosemi, which is a Silicon Valley team of PhDs who specialize entirely in photonic integrated circuits. They are signaling very clearly that upcoming chip generations, like the MI500, will begin transitioning away from traditional copper electrical networks and heavily toward these light-based co-packaged optical networks.
Okay, but firing that translator, the DSP has to create a massive engineering headache, right?
It really does.
Because if the translator's gone, the two sides of the system still have to understand each other.
What's fascinating here is the concept of the language barrier in signal modulation.
Okay, break that down for me.
So historically, the DSP acted as the universal translator between the electrical domain on the motherboard and the optical domain in the fiber cable. It could effortlessly handle different speeds, different error rates, and different formats.
Right.
But in a co-packaged optics setup, because you remove the DSP to save power, the electrical side and the optical side are now essentially hardwired together. They have to run at the exact same rate.
Wait, hold on. You're losing me a bit here.
Okay.
What do you mean they have to run at the same rate? Don't they already speak the same basic digital language of ones and zeros? Why is this such a brutal physics problem?
Because physically, they do not speak the same language.
Oh.
The optical industry has spent years universally agreeing on a standard called PM4 for transmitting data over light.
Okay.
PM4 transmits 2 bits of data per symbol. But the electrical side, running on the physical silicon motherboard, uses a completely different standard called PM6, which translates to roughly 2.585 bits per symbol.
Okay, I get it now. So it's like trying to mesh two heavy machinery gears together, but one gear has 4 teeth and the other gear has 6 teeth.
Exactly.
If they're spinning at billions of times a second and you don't have a transmission, the DSP in the middle to synchronize them, they aren't going to mesh smoothly. They're just going to grind against each other and shatter.
When those metaphorical gears shatter, it results in massive data errors.
Ah.
When you transmit data at these blistering speeds, errors are just an inevitable fact of physics. The signal naturally degrades and gets noisy.
Right.
In the past, the DSP would handle what is called forward error correction. It acted like an editor, constantly cleaning up the messy signal, fixing typos in the code before the data was sent out into the network.
So without the DSP, who is fixing the typos?
No one.
Oh, wow.
Yeah, with the degraded signal-to-noise ratio of a PAM6 electrical signal trying to interface directly with a PAM4 optical signal, correcting those data errors becomes incredibly difficult.
You're just flying blind.
You're essentially flying blind, relying purely on the raw, unassisted physics of the connection to perfectly transmit the data.
So what does this all mean for the timeline? If the physics of aligning KM4 and PAM6 are this brutal, are we putting too much faith in these 2027 deployment promises?
It's a huge debate right now.
Because we've got independent research firms like Semi-Analysis and reports via O'Daily claiming that because of these exact issues, specifically the nightmare of integrating these lasers directly into custom-built ASICs mass adoption might be severely delayed.
Right.
We're seeing predictions that NVIDIA's massive 800-volt DC architecture and CPO production might get pushed to 2028 or even 2029.
Because the leap from pluggable cables to co-packaged optics is not just an iterative update, like putting a faster engine in a car.
It's fundamentally different.
It is a fundamental redesign of how the car operates on a molecular level. Integrating fragile optical lasers directly into custom-built ASICs is incredibly delicate work, and manufacturing yields are a real concern.
Right.
However, the market is severely divided on these delay predictions.
Right, because the hardware vendors are telling a very different story to their investors.
According to recent financial channel checks via KuCoin, when analysts speak directly with AMD's networking partners on the ground, those partners are reporting no indications of CPO scale-up delays. They are directly pushing back on those third-party delay reports, suggesting their engineering teams have the manufacturing yields under control and the deployment timelines remain fully on track.
And obviously, we aren't here to pick sides or endorse one company's timeline over an independent analyst's timeline. We are just looking at the tug of war happening in the source materials.
Exactly.
On one side, you have researchers looking at the brutal physics of missing DSPs and mismatched signals, predicting multi-year delays. On the other side, you have the hardware vendors insisting they have the engineering solved.
But either way, it is a high-stakes race. Because whoever figures out how to mesh those gears together first, efficiently and at a massive scale, is going to completely dominate the next decade of infrastructure.
Right.
You simply cannot build a 200,000 GPU cluster without solving this specific optical bottleneck. The energy grid won't allow it, and the physical space won't allow it.
So, to bring this all back home to you, the listener, why should you care about DSPs and mismatched gear teeth and the power bills of a 72 GPU rack?
It's a good question.
Because the capabilities of the AI you are going to use tomorrow, whether you are asking an agentic AI to completely manage your calendar, write the code for a complex website, or discover a new pharmaceutical drug, those capabilities are entirely limited by how fast and efficiently these data centers can pass information around today.
Absolutely.
The AI brain is only ever going to be as good as the nervous system supporting it.
And if we look at the trajectory of the hardware, it raises an even more pressing concern for the future.
Oh.
What's that? Well, we've spent this entire time unpacking the networking bottleneck. But some of the financial reports briefly highlighted that raw memory capacity remains a massive part of the total cost of ownership for these racks.
Right.
AI models are growing exponentially larger every few months. This raises a critical, really provocative question.
Okay, lay it on us.
Could the industry hit a physical and economic memory wall before we even finish solving this networking crisis?
Yeah, really, a memory wall.
We might reach a point where we simply cannot afford to manufacture or power enough physical memory chips to hold these massive models.
Wow.
If that happens, it might force the entire software industry into a desperate, complete rethink of how AI models are compressed, optimized, and built from the ground up.
Completely new way of building the brain just to survive the limitations of the nervous system and the memory banks.
Exactly.
It really makes you realize that the future of AI isn't just about making the chips smarter. It's a brutal physical war to figure out how to let them talk without burning down the power grid.
It certainly is.
Well, thank you so much for taking this deep dive with us today. We'll catch you next time as we continue to unpack the forces shaping our world.